Let us think about the idea of what would be allowed rotations as governed by the requirements of symmetry. Let's imagine some 2 points, A and B. These are lattice points, so they are joined by a lattice vector A1. And we have to impose the requirements of translational invariance so that we can understand what kind of angles will be allowed. Now, assuming we have these 2 points, A and B, we can generate some 2 other points, A prime and B prime, by 1, rotating A about B by an angle phi. And alternately, we can get the point B prime by rotating B around the point A by an angle minus phi. Now, since A and B are lattice points, it implies that A prime and B prime will also have to be lattice points, since when we rotate them, translational invariance requires that. So the distance A prime B prime will be a multiple of a vector. So that is why we have the absolute value of B prime A prime equal to P times A1, where P is always an integer. Remember that lattice points are always defined in terms of n1, n2, and 3, which are always members of the integer group. Now, also from geometry, if you think about the fact that there are triangles in a triangle, and we have a right angle triangle here in between B, A prime, and B prime, and alternately also between A, B prime, and A prime, we also have another right angle triangle. We can say that the distance B prime A prime will be given by A1 plus 2 times A1 sine phi minus pi by 2, or A1 minus 2 times cos phi. If we solve these two expressions for cos phi, we end up with cos phi equal 1 minus p over 2. But the interesting thing is that the cosine always ranges between minus 1 and 1. So what we have on the right can only take the values that are within this range. So what do we get when we impose this condition? We get a simple table that illustrates to us mathematically what these allowed angles are. So let's take a look at that table. So these are the angles that you expect to find. So when P is minus 1, the cos phi will be 1, and we'll expect phi to be 0 or 2 pi. So this is a rotation by a full circle. Again, when P is 0, we have 2 pi by 6 as the allowed angle. When P is 1, we have 2 pi by 4, again 2 pi by 3, 2 pi by 2. So we can see that we have only a finite set of allowed angles that will be what can be used to operate on a lattice and end up with a lattice mapping back to itself, satisfying the requirements of translational or symmetry. And now, as an aside to this, we talked a bit about the idea of a Wigner-Seitz cell. So here I'm simply illustrating the same idea by showing you what I meant by its construction. So if we have a set of lattice points, we can draw lines joining all the neighbors to one of the lattice points, and then we bisect these lines with a perpendicular bisector. The space that is enclosed by all of these bisectors is what we call the Wigner-Seitz cell. So this is in 2D. In 3D, it's going to be a many-sided polygon, and so on and so forth.